In the previous video, we have successfully implemented the push functionality, which will basically add the new value at the end of the singly linked list, right? In this video, let's try to perform an operation which will basically delete the very last node we have inside the singly linked list. So that operation is nothing but pop operation. So we already know the very last node is nothing but the tail node we have inside the singly linked list, right? And we have to delete that node from the singly linked list. That basically means that inside the singly linked list representation that we are maintaining, right, we are maintaining the head node and tail node. Along with that, we are also maintaining the length of the singly linked list. So we have to make sure that we are making proper adjustments in these three variables according to the cases that we are seeing. Here, one thing that you have to remember is basically deletion doesn't mean that we are actually freeing up the memory. So what exactly we mean by deletion is in the case of singly linked list, right, every node will have the reference of the next node, right? That means if you take the reference of the node true, it will be available inside the node with the value code. Similarly, the reference of the code will be available on the node 10. Similarly, the very last node we have inside the singly linked list is false, right? And this reference will be available inside the node -10. So to delete the node false, that is the very last node we have inside the singly linked list, what exactly we will do is the next that we have inside the node -10, that we will update it with null if you are following Java or JavaScript based implementation. In the case of Python, we will update it to none. Okay, so in that way we are losing the track of the very last node because we have deleted the reference. That means that that node is no longer available inside the singly linked list. And remember that since we are deleting the very last node, whatever the tail node that we had previously will no longer be the tail node. We have to update the last but 1th node as the new tail node of the singly linked list. Okay, so that is a simple way how we actually delete a value inside the singly linked list. What exactly are the different cases that could appear when we are trying to perform the pop operation? Let's assume that user is trying to perform the pop operation on a empty singly linked list. That means that there are no nodes at all inside the singly linked list. That means both head and tail are empty and length is 0. In that case, obviously, since we don't have any values, we will not be able to perform pop operation. In that case, we will simply return null if you are implementing Java or JavaScript based representation, and if you are following Python based representation, we will simply return none. Okay, so that is the first case. In the second case, where we have only one node inside the singly linked list, in that case, since we have only one node in the singly linked list, right, let's assume that only one node is 10. So obviously head will be pointing to this node and we will also have the tail at the same node, right? So the only node is available inside the singly linked list and we have to delete that only one node, because as part of the pop operation what we do, we will delete the very last node. When we have the only one node inside the singly linked list, pop operation, we will have to delete that only one node. In that case, since we are deleting this, the singly linked list will become empty. So how will we exactly represent an empty singly linked list? To represent that, head we will update it to null or none. In the case of Python we use none. In the case of Java or JavaScript we will simply use null. Similarly, the tail also we will update it to the similar way how we have updated in the case of head. And there are no values inside the singly linked list at all, right? In that case we will simply update the length to 0. So in that way we are making sure that there is no inconsistencies in the head or tail or length that we are maintaining for representation of a singly linked list in our implementation. And the third scenario is obviously we have more than one node. So if we have more than one node, this is the classic example, right? So in that case, head will be somewhere and tail node will be somewhere. So we have to make sure that we are deleting the very last node. So how will we actually delete is, let's take a small example where we have, let's say, 3 nodes available inside the singly linked list. So this is the head node and this is the tail node, and let's assume that 10 code and true are the values present inside the singly linked list. So according to the algorithm that I have explained, how will we delete the last node? We will simply go to last but one node, that is we will go to the node code, and there we have the reference of the true inside that node, right? And we will simply assign it to null or none based on the choice of the programming language that we are using. Okay, so as part of the first step, our aim is to reach the last but one node, and there we will update the next to null, and whatever the node that we have deleted, right, in that way we are losing the reference of the node true. So the connection has been removed. As a result, the value has been lost from the singly linked list. But the thing is, the tail is still available at true only. So, and that is not part of the singly linked list. So we have to make sure that last but one node is becoming the tail node. That's why in the case where we have more than one node, we will go to the last but one node. There we will update that nodes next to null or none based on the choice of the programming language that we are using, and we will basically decrement the length by 1 because we are deleting the node after all from the singly linked list, and we have to make sure that the tail node is getting updated to last but one node. Okay, so that is the process of performing a pop operation on a singly linked list. I hope you understood. Now let's write the pseudocode for the same. So to write the pseudocode, obviously first what we will do is we will write a function called pop function. Obviously it will not take any argument, and it will basically delete the very last node, and it will return that node back to the user. So as part of the first step, what we will do, we will check if the singly linked list is empty. If it is empty, what we will do, we will simply return null or none based on the choice of the programming language that we are using. So this is the case where we have the singly linked list is empty. The second case is where we have only one node. That means if the length of the singly linked list is 1, that means whatever the length variable that we are maintaining, right, if the value inside that is 1, the singly linked list has only one value. Besides this, one more comparison that you can do for checking if the singly linked list has only one value or not is because when we have only one node inside the singly linked list, head will be at the same node and the tail will also be at the same node. So you can simply do head is equal to the tail as well to check if the singly linked list has only one value or not. If at all, if that condition is matching, how we will delete the last node? We will simply update the head that we are maintaining. We will simply update it to null or none based on our programming language of choice for implementation, and inside the tail that we are maintaining, we will also make it as null or none, and the length will become 0 because there are no nodes inside the singly linked list after deleting. But in the end we have to return the node that we have deleted, right? But that's why before performing or updating the head to tail to none, just read the tail node, okay, and store it in some variable. In the end, return that old tail. Okay, so that is the case where we have only one value inside the singly linked list. Now let's just try to perform the pop operation on a singly linked list where we have more than one node. So otherwise, so the logic will be simply otherwise. That means that we haven't matched the first two cases. That means that we have more than one node inside the singly linked list. So in that case, what we will do, we will go to last but oneth node. So first process is to check read the last but oneth node. So we will start at the head node and we will keep track of the previous variable, and using that previous variable we will go to the last but oneth node. Once we go to that node, right, how will we delete the last node? We have the reference of that node in the last but oneth node, right? That is available in the next of the last but oneth node. So we will update next to, we will simply update it to null or none based on our programming choice of implementation, and we will simply update tail to last but oneth node, because the reference of this node has been lost in the last but oneth node because we have updated it to null or none. So this will no longer be the tail node. So we have to make sure that tail node is getting updated to the actual tail node or the very last node we have in the single linked list, which is nothing but the last but oneth node. And here we will again decrement length by 1, because after all we are deleting one value from the single linked list, right? So since that value has been deleted, we have to make sure that we are making proper adjustments in length as well. Since we are deleting one node, we will decrement the length also by 1. In the end, just like how we read the tail node, we will first read the tail node here in this case as well, so that in the end we can return the old tail of singly linked list, which is actually getting deleted from the singly linked list as part of the pop operation. So this is the pseudocode for implementing the pop operation on a singly linked list. So just remember that there will be 3 cases. First case will be empty singly linked list, and the second case will be where we have only one node inside the singly linked list, and the third case is where we have more than one node. So according to that case, we are handling and we are making sure that head, tail and length which we are maintaining in our single linked list in presentation are getting adjusted with the proper values. Okay, now that we have seen the pseudocode, let's convert this into our programmatic implementation. Okay, so inside the single linked list class that I have written earlier for implementing push and traverse functions, in that same I'm going to define a function called pop. So whenever you are trying to perform the pop operation on a single linked list, there could be 3 cases. One, either the user is trying to perform the pop operation on a singly linked list which has no nodes at all, or the second case could be user could try to perform the pop operation on a singly linked list where we have only one node. And the third case is pop operation being performed on a singly linked list which has more than one node in the singly linked list. So as part of the implementation that we are going to do, we need to honor these 3 cases. Now let's try to write the implementation for all these 3 cases. So as part of the first case, I'll try to write the logic for pop operation on an empty single list. How will we know if the single linked list is empty? In the case of empty single linked list, both head and tail will be pointing to null, or you can also compare the length value to 0 so that you are sure that the single linked list is empty. So I will follow with head being compared to null. Okay, if it is null, since the single linked list is empty, we can't do anything, right? So we will simply return null. Okay, we have handled the first case where pop operation is being performed on an empty single linked list. Once we are done with this, there could be other scenario also, right? So the other scenario is basically where pop operation being performed on a single linked list which has only one value. So to honor that case, what I will do is, when we will have only one value, if both head and tail nodes of the single linked list are pointing to the same node, then we are sure that there is only one node. Otherwise, you can also check with this dot length should be equal to 1. Then also you can check, you can basically confirm that the single linked list has only one value. So here I will simply compare both head and tail are same. That means we have only one node in the single linked list. So as part of the pop operation, we need to return the node that we are going to delete. So let me just read that tail node into one variable so that in the end we can return that. So what I will do, I will simply do this dot head or tail, because both of them are pointing to same, right? Same node. So you can either read head or tail, it will be pointing to the same node, so it really doesn't matter. Now if we try to delete the only existing node in the singly linked list, head will become null and tail will become null and length should become 0, indicating that the list has become empty. So to honor that, I'll simply update this dot head, I will update it to null. Similarly, this dot tail, I will update it to null, and I will also have to make length also to 0. Okay, so if we have to delete the only existing node, that means the singly linked list implementation that we are doing will become empty. So what we are doing, we are simply making head to null and tail to null, and the length also we are updating to 0. In the end, we need to return the node that we deleted. The node that we deleted is tail node, right? So we will simply return tail node. Okay, we have handled the second scenario as well. Now the third, if none of these cases match, that means that we have more than one value in the singly linked list, right? So to support that, so if you remember the pseudocode that we had discussed, if the singly linked list has more than one value, how will we delete the tail node? First, we will have to reach the last but one node, right? Because singly linked list is only one way traversal is possible. So we should start from head node and we should reach the last but one node of the tail node. Once we reach such node, we will simply update the next of that node to null so that we would have deleted the tail node itself. Okay, if you have any confusion, go on to codingpal.org and try to visualize it so that you will have a better understanding. Okay, once you understand it, come here, the implementation will be very easy. So to go on to such that last but one node, I'll write the logic now. First what I will do is I'll simply create couple of helper variables. First variable is current node. This I will be assigning it with the head we have. Along with this, let me take the tail node also, which we have inside the variables this dot tail. Along with this, I will create a new variable called new tail. Okay, new tail equal to, I will assign it with the head node in the beginning. Okay, so by the time whatever the logic, iteration logic that we are going to implement in 1 minute, so this new tail variable will be pointing to the last but one node. So to perform such way, what I will do, I'll simply write a while loop as long as the current node that we are processing is not equal to the current tail node. That means as long as whatever the node that we are processing is not equal to tail node, that means this logic will break at the tail node. So what we will do simply here, I'll simply update new tail to the current node that we are processing, and to proceed further, I will update the current node to current node dot next. Okay, in this way, since this loop is going to end at the tail node, we would have the access of the last but one node in the new tail variable that we have defined here. Okay, so once this loop completes, we need to adjust the next to null, right? That means we will simply make new tail dot next equal to null. Okay, that means we have deleted the last node, that is tail node, but the tail is still pointing to the deleted node itself, right? So whatever the tail reference that we have inside the singly linked list should also get updated to the new tail reference here. So I'll simply do this dot tail equal to new tail. Ultimately, we have deleted one node from the singly linked list, so the length should also decrement by 1. So this dot length equal to this dot length minus 1. Okay, in the end, we need to return the node that we have deleted, which is nothing but the tail node. So the tail node we have read in the beginning. So I'll simply return tail node. Okay, in this way, we are going to implement the pop operation honoring 3 scenarios. Okay, just to recollect, if the singly linked list is empty, we can't delete the tail node, so we will simply return null. If the singly linked list has only one value, in that case we will update both head and tail to null, because whatever the only node that is existing, that also we are deleting, and we are making the length to 0. If that is not the case, we are going to last but one node, and we are making that node as a tail node, and we are updating the next of that node to null, so that we are losing the reference of the tail node. In that way, we are deleting the tail node of the singly linked list. Okay, since we are deleting a node, we are reducing the length by 1. Okay, this is the implementation of pop operation. Now let's try to execute it and see if it is able to pass the scenarios that we have here. So in the singly linked list that we have here, sll.push, let's put one of the floating point value also. Okay, now in the singly linked list that we have here, the first value that we are pushing is 10, so the head node will be 10, and the last node that we are pushing is 10.134. so the singly linked list will preserve insertion order, right? So the values that we have here, 10.134, this is the tail node of the singly linked list. So if I simply perform pop operation first, and after that if I traverse, I should basically see the values 10 codingpile.arg and true being printed, because the tail node is being deleted. So let me just to confirm, head node and tail node also are pointing to the valid ones. Let's also log console.log of sll.head.value along with this sll.tail.value and sll.length. Okay, so after traversing, let's just put a separator, console.log. Okay, now if I execute this node singly linked list.js. okay, so as part of the pop operation that we are trying to implement here, it will delete this node. Now the resulting list has 10 codingpile.arg and true. So if I call the traverse function on that list, I should basically see this. In the remaining list, the head node is 10 and the tail node is true. So as part of this console.log, I've got 10 true and 3. 3 is nothing but length, which is nothing but the total number of values we have in the singly linked list, which is 3. Okay, this is the case where we try to perform the pop operation on a singly linked list which has more than one value. Now if I try to perform the pop operation on a singly linked list which has only one value, that means both head and tail should be pointing to null. Here we are trying to print dot value, right? We will basically get the null pointer exception. So I'm simply removing dot value reading here. So if I execute this now, ideally we should not print anything because the only existing node 10 is being removed. So head and tail will be pointing to null and length should become 0. Okay, so as part of this traverse, we haven't printed anything. After that, we printed this separator, and as part of the head and tail logging, we've got null, null, and 0. Okay, now if we try to perform pop operation on an empty single list also, we are simply returning null, right? We are not doing anything. And basically, if we traverse it, we should basically see null, null, and 0 only. So okay, we are seeing null, null, and 0. If at all, if you want to use the popped value in your logic, you can simply do const popped value, and you can use it in for logging or whatever you want to do. You can do that too. Okay, you can simply put console.log popped value. Okay, let me just copy this and let me just okay, now if I pop it, if I perform the pop operation, I should basically see the value that is being popped, that is true. Okay, okay, if you see here, popped value is true. Okay, as part of the second statement. So basically, whatever the return value that you're returning, if you want, you can capture it and use it however you want. But however, my main concern here is to show you guys how the values are being manipulated here with respect to head node and tail node, and what is the length. Are we maintaining the consistency of these variables throughout the implementation? That is my major concern. Okay, but this is how we actually perform the pop operation in a single linked list. Now what I would want you to do is, I would want you to perform multiple pop operations continuously, and try to perform the push operation after pop operation and try to see what exactly is happening, so that you will have a better understanding of these operations. All right, now we have already implemented the pop operation as well, right? In this video, let's try to understand time and space complexities involved in the pop operation. So obviously, let's just try to divide it into best case as well as the worst case scenarios for both space and time complexities. So when will the best case of pop operation will actually occur? When the singly linked list is empty or it has only one node inside the singly linked list, because we don't have to go to last but one node inside the singly linked list, right? That's why the best case will obviously will occur it when we have only one node in the singly linked list or empty singly. In that case, what exactly we are doing? In the case of empty, we are simply returning null or none based on our programming language of choice. In the case of when we have only one node, we are updating the head node with the null or none and tail node with the null or none, and length also we are decrementing by 1 or we are making it to 0. So obviously all these operations are simple assignment operations, right? And these assignment operations will take 1 unit of time. As a result, in the best case scenario, the time complexity will be order of 1. Okay, now let's talk about the worst case scenario. Let's assume that the singly linked list is that we have, on which we are trying to perform the pop operation, is something that like you see on the screen, where let's just assume that we have n number of nodes, right? In that case, what exactly we are doing? We are going to last but one node. That means we have to start at the head node and we have to go to last but one node. That means that we have to run a loop for going till the last but one node. That loop we are running it for n minus 1 number of times, right? So in that case, once we go to that node, we are updating the next appropriately so that the last node is getting last. And after that, we are updating the tail to null or none. So obviously, the overall time complexity in the worst case, where we have n number of nodes, the major operation is to go till last but one node. For that, we are running a loop and it is running n minus 1 number of times. As a result, we can say the time complexity will be order of n minus 1, which is nothing but order of n as a worst case time complexity for pop operation. Okay, so that is something that in terms of time. So let's talk about in terms of space. So we already have the head and tail and length inside our singly linked list representation. So in the best case scenario, when we don't have any values at all, or when we have only one value, we are simply updating the head with null or none, and similarly tail also getting updated with null or none, and length we are updating it with 0. And these are simple assignment operations, right? And obviously assignment operations will not take more than unit amount of memory internally. As a result, in the best case, the time space complexity will be order of 1 only. Okay, now in terms of worst case space complexity, yeah, we are sure that we are running a loop for n minus 1 number of times, but we are taking a help of a single variable for keeping track till the last but one node. We are simply using a single variable, and that variable itself is keeping track of the previous node. In that way, we are going to last but one node. Obviously, since it is a single variable, it will take constant amount of memory. And after that, the tail node is getting updated to last but one node, and length is also getting decremented by 1. These assignment operations will obviously take constant amount of memory only. As a result, the overall space complexity in the worst case also, where we have more than one node, or where we have n number of nodes inside the singly linked list, even though we are running a loop for n minus 1 number of times, the space complexity will still remain constant only, because we are simply using a single variable for going till the last but one node. Okay, so that is the space complexity in the worst case scenario for performing the pop operation on a singly linked list. Okay, so that is how we calculate the time and space complexities, and that is how we exactly implement the pop operation for various cases that can come while implementing. Okay, in the next video we will get on with implementing the next functionality on a singly linked list. Okay, I'll see you there.